Whenever I get into trouble, and I do get into trouble, I think I went to Joe in trouble as opposed to men in trouble, I call Mark. He's one of the best guys on the planet, and every time he speaks, I learn something spectacular. And so I've heard a version of this talk, and it gets better and better. So please give an incredibly warm welcome to my favorite engineer. Okay, there are other engineers I like, but not as much as Marc Rosenbaum.
Joe, do you know how to turn this on? Because I can't see it.
It's on.
It's on? All right, that's great. There's probably a machine here to click this thing, but I can't see it.
MIT.
It's just got two arrows, so I should be able to figure this out, right? 50% chance, like the USB, when you put it in, a 50% chance you'll get it right, but it's always wrong. Well, thank you for your attention this morning. I want to say first, just say something about, take a minute and just think about how lucky we are, right, to be here, to be in this field that we're in, which is very broad. People do very different things. We have a real community in this work, and most people don't have this in what they do. And so we're part of this community that we learn from, we support each other, we make sure that people get home after they've imbibed too much. We're really lucky, we're fortunate. Just think about that for a second. I mean, I've been in this for 45 years, and almost all my best friends come from somehow from this work. All right, so in the sort of twilight of my work career, my goal is to try to teach people things about fundamentals rather than some whiz-bang, here's the state of the art of this and that. Because I think with the advent of incredible software and incentive programs, form follows incentive, certification programs, sometimes we lose sight of some of the basic physics that drive our buildings. So that's what today is about. If you think this is useful at the end of the session, tell Joe and Betsy, because next year I'd like to do one on fundamentals of solar energy. All right, so let's get going. The title of this slide comes from Andy Shapiro, who's very pithy about things. It's like, before we talk about something, his question is, why bother? And I think it's a great question. Why do we care about this? So one of the things we care about is integration of renewable energy into the utility grid. And these are two load profiles, winter and summer, typical. Winter has double humps, and summer has a single hump, and it's driven by space conditioning, heating and cooling. This is, thank you to Lisa White for these next few slides from FIAS. Thank you all the FIAS people. We've had a long and hopefully fruitful relationship in both directions. This is the California demand trend for electricity, and you can see that it peaks at around 6 at night. It's a summer day, it's an actual day, and cooling is driving this, right? And then there's the renewables, which is mostly solar. So the big boa constrictor swallowing its prey in the middle there, that is PV. And you can see there's other things there. The lower line is wind, and wind is usually low during the day and then picks up again at night. So more wind is going to help balance renewables penetration into the utility grid. But that's the PV, which is the big driver here. And then together, that's how the PV suppresses demand in the middle of the day, because it's feeding into the grid, and then they can turn off some of the generators. However, what happens is, towards the end there, California has to bring on 11 gigawatts of power. That's a big number. A gigawatt is bigger than a mega. It's like giga. So that's like 11 full nuclear power plants coming on in 3 hours. And as a comparison, the whole Massachusetts solar capacity is around 3 gigawatts. Okay, and Massachusetts has been a very favorable state to put solar in. So this is a real problem. We've got to bring on a ton of capacity, or actually 11 gigawatts, in 3 hours. And the more this happens, the worse the grid is going to be able to handle it. Just so you don't think that this isn't just a California problem, there's New England ISO, and it's the same thing. It's this, the renewables fill the need during the day mostly, and then bammo, when the sun goes down, the grid has to come up. The other thing is, not all hours of the grid have the same emission profile, right? So you can look at this. This is a snapshot, again, I got from Lisa. This is hourly through the year, and this is carbon emissions from utility generation, and this happens to be Chicago. And this is a snapshot from 2019. By the way, Lisa and I looked at this thing, and we both kind of scratched our head, like, how come the greenest ones are summer peaking? And I don't know the answer to that, but I have a guess, which is probably wrong, which is that if the grid is mostly coal as the base load, and their peakers are natural gas is cleaner than coal. So that might be why this profile looks like this. Lisa sent me, and I didn't have time to put it into this presentation, some future ones from other places, you know, projections of the grid, and it looks very different. Okay, so what are our strategies to help with this? Well, the first thing, the fundamental thing, is building load reduction. And thermal, I think people have their heads around thermal load reduction, but it's also electrical. So you want to look at all the things that use energy in the building. Then grid interactive control. So there's more and more situations where the utility will pay you to let them turn off stuff in your building to shave the peaks, right? And then the third thing is shift the load in time so it doesn't happen at the peak. And so energy storage is a load shifting strategy. And here's a classic energy storage load shift. This is ice storage. So you get an ice making chiller and tanks, and you make ice, but the way this has been applied traditionally is you make ice at night, because that's when the grid baseload energy is cheap. So this is really an economic shifting, but you're going to see that we can also use this to peak shave. So that's a very classic way to shift load. And I'll say one thing parenthetically about that. I'm a consultant, so I like to be billable by syllable, longer words. Never use a short one when a long one will do. When you store ice, you're able to run your coils colder. And if you look at, if you do loads for very energy efficient buildings, passive houses, you're finding that they're all cooling load dominated, even if they're in some place where people shouldn't live, like Duluth. So the colder the coil, the more moisture you get out, and your sensible heat ratio shifts. And you know, I think we have an emerging issue in more efficient buildings with cooling, and the sensible load we keep driving down, better glass, better lighting, things like that. And then we haven't really done that much to the latent load because people are still breathing in the building and cooking and taking showers. Okay, another why bother. Net metering, where the utility lets you essentially send energy back to the grid at retail, is a political artifact. It is not a physical fact of nature. This is something that people have agreed on, and they are unagreeing about it, right? So someone I talked with last night at dinner said, oh, we have 15 kilowatts of PV. Someone in California. I said, I thought California kind of destroyed net metering. Yeah, we got it in, and we pulled some favors, and we got it in before that shift. So net metering is going away in a lot of places. It's not guaranteed. And once it goes away, the value of the energy that you're sending out and then need to bring back in, using the grid as the battery, that value goes down. So the more we can self-consume the energy that we make renewably on site, the better off we are and the better off the grid is. And then just plain resilience. What happens when the grid goes down? And this is an event that happened a couple of years in Massachusetts. A good deal of the state was out after an ice storm. You notice that those little things at the lower right-hand corner, those are islands. I live on the one that says Dukes, that's the county, Martha's Vineyard. It's a small island off the coast of reality. And apparently, we were not out because we have no color in those two islands. So I don't know whether that means they don't count us or we were just so resilient. We got 4 cables that go to the mainland. That's it. And one of them's broken. We're even more vulnerable than the mainland to these outages. So, you know, if your building doesn't really change a lot when the grid goes down, that's a good thing for you. All right, so what everybody's focusing on now is electrical storage batteries. And electrical storage batteries are pretty cool. They're very flexible because you can use the energy to do anything in the building. They definitely provide grid outage resilience. They provide load shifting and peak shaving. So you can make your energy with your PVs during the day and then use it some other time during that cycle. And you can, if you're getting demand charges for your peaks, like we do in commercial accounts, then you can shave your peaks by using storage. You can also boost the amount of site-generated energy that you consume on site with a battery. So in this particular chart, there's 3 lines. The middle line is a net zero annual house. It's where the PVs make the amount of energy that the house uses in a year. And over at the left, with no batteries, typically, at least in my part of the world, because this, you know, the climate's different in different places, if you've got a net zero house and you measure how much you're actually using contemporaneously on site, it's about 1/4. And I have measured this in my own house. If you add batteries, and so on the horizontal axis is a dimensionless term, which is kilowatt hours of storage divided by the actual daily average kilowatt hour demand. If you add batteries, then you charge the battery and then you use that energy on site instead of sending it to the grid. And so I've got that 65% is where the battery storage is equal to the average daily usage of the building, okay? So in this particular case, if I look at my own house, we use about 4,000 kilowatt hours a year. It's an all-electric house. It's a small house. We actually now use almost 6,000 because we have an electric vehicle. But that's because my system makes 6,000, and Eversource, I had a $1,500 credit with Eversource, and Eversource seems to refuse to write me a check for that. So I'm using it instead of gasoline, and now we are zero energy. But if I had an exactly net zero house and I put in 1 Tesla Powerwall, which I would never do because Elon Musk sucks. Then I would go from about 1/4 of the energy used on site to about 65%. Now, if you're using a battery that way, the problem is, one is they're expensive, but the capacity drops over time. So if you use it as just backup when the grid goes out, battery will last a long time. But if you're charging and discharging daily, you're going to get a number of cycles, and the capacity is going to drop. The other thing about a battery is, again, it's a, I believe Andy would call this a widget. Is that the proper term? It is a widget, so it doesn't provide any inherent resilience that a really good building provides, right? It's just a thing in your building that provides electricity when the grid goes down. I think batteries are probably best in distributed microgrids. So I don't think they're best in like huge utility banks, in which case they have to go out through a bunch of transmission lines. And I don't think they're probably best on a house-by-house basis. That's just my opinion. Most of my opinions are wrong. Often mistaken, but never in doubt. That's one of the things I learned at MIT. I think the future for homeowners is vehicle to building. And the image on the left is the first car share in the country, in Colorado, with vehicle to building capability. So you're using the battery in the car. And on the right, oh, by the way, that car on the left is a Nissan Leaf. And I owned a Nissan Leaf at one point, and I hope I'm not offending people, because I'm sure there's at least a couple of Leaf owners here. A Nissan mile, I learned, is only 4,000 feet. Shittiest car I ever owned. However, I now have a Chevrolet Bolt, and I have a new battery because of the battery recall. So, and that little car is the equivalent of 5 Tesla Powerwalls, 5 of those boxes. There's 66 kilowatt hours in that car. Don't I want to use that instead of buying separate batteries? You know there's a hurricane coming. You don't want to be in New Orleans. I mean, but then ultimately, you probably, when it finally hits us, we're going to look worse. Yeah. So I think that's the future. And you know, I believe the Ford Lightning, the F-150 Lightning, will hook up to a building. So that's where it's going. I am heating climate centric, so you can flip all this and change the word to cooling. But heat is the biggest load. So here's my little superinsulated house. We had a snowstorm in February in 2016, completely covered the PV system. And typically, if you're in climates like mine and you get this kind of storm, and then you get some thaw, but there's enough snow on the roof, then it melts and ices in. And I have one client, the first actual zero energy building I did in New Hampshire, where the PVs were covered and iced in for over 5 weeks. So, and you weren't going to get it off without destroying the panels, you know, when it really locks in there with ice. So here's 3 days, no PV, small house, super insulated, 63% of the energy used went to heat. Okay, so heat is the thing that we're trying to provide when the grid goes down. So let's start talking about some of the factors that matter with thermal storage of energy. And I want to introduce you to the time constant. So the time constant tau, on this graph, you see Tmax. And let's just think that Tmax is the set point temperature you want in your building. So I'm going to call it 70. If I was passive house in German, I would only have to call it 20C, which is 68. Let the Germans freeze. I want mine at 70. All right, so Tmax is 70. And TU on the is at the bottom, U stands for outside. U? I don't get it either. Okay, so if you don't put any heat into this building and you let it coast down to TU, at the point where it has dropped 63% of that differential, and that has to do with logarithms, and I'm not going to explain that, that's the time constant, the time it took to drop 63% from the original temperature to the outside temperature. Hold that thought. So what is a building time constant? You can calculate a building time constant the thermal capacity of the building divided by its heat loss coefficient. So what's thermal capacity? It is the amount of energy, and I'm using English units because I am American, and we have 2x6s, not 50 by 150 millimeter studs. You notice how many things in metric really are just inches? Rounded up by 25 instead of 25.4. Once a long time ago in the Whole Earth Review, J. Baldwin wrote the case for each of the units, and he had English units in one column and metric, and there was one line in metric. Everything's divisible by 10. And then the English units, there was a whole bunch of reasons why they are useful. Anyway, how many BTUs does your building need to raise it 1 degree Fahrenheit? Or drop 1 degree Fahrenheit? That's the thermal capacity. So a building that's more massive takes more BTUs to change its temperature. Does that make sense? Stop me when I really stop making sense. I don't mean like the big suit of David Byrne. Okay, divide that by the heat loss coefficient, BTUs per hour per degree Fahrenheit. And if you actually do unit cancellation, which is something if you're old you learned to do, so you didn't get the wrong answer, you get hours. You get time constant in hours. A range of thermal capacity for light frame wood buildings is between 5 and 7 BTUs per square foot per degree F. A range of heat loss coefficient, and the units may not be familiar here, 1/8 to 5/8 BTUs per hour per square foot. But here's my example. A 2,000 square foot house, maybe somewhere between 15,000 and 75,000 BTUs an hour. Yes, passive houses are lower, and really, really bad houses are higher, okay? But most of the buildings that you've ever seen are in this range. So far, so good? You have to trust me on this one. So a time constant of light frame houses would be somewhere between 10 and 50 hours, depending on the heat loss of the house. It turns out I found a paper by someone named John, not Straub, and Al. I have no idea who Al is and why he uses French instead of John and Al, but it has to do with metrics. They looked at Ecobee thermostats because they didn't know Blasnik, so they didn't look at Nest thermostats. And they estimated from the data from the thermostats, the smart thermostats, that the majority of US time constants were in the 15 to 55 hour range. So I'm pretty close with my sloppy math. All right. So now, what does this mean? It's a good question, isn't it? What does this mean? Why bother? Well, that's the wrong question. We already used that question up. Okay, so let's say we have a house and it's at 70 degrees and outside it's 10. A balmy day in Duluth, LeBeau. And what I've plotted here are two curves. The lower one is kind of normal thermal mass. I picked 6 BTUs per hour per degree F per square foot. And the red line is double the thermal mass. And you can see the horizontal axis is heat loss. So if we take the normal house, the blue line, at 75,000 BTUs an hour, heat loss, the time constant is 10, and it takes 5 hours to go from 70 to 50 when the heating system's turned off. 5 hours. The time constant is 10. It takes 5 hours, if you do this math, for it to cool down 20 degrees. And this is the house I grew up in suburban Boston. Like, we used to joke that when we had, one Honeywell thermostat, we used to joke that my mom would turn it down when we went to bed, and as she was turning it, the thermometer was dropping. Right? Uninsulated wood frame building. Now it's probably 130 years old. My grandfather grew up in that house. Single glazed windows, steam radiators. You could either freeze or burn, like within inches. So that's a really bad house. Conventional house at 15,000 BTUs an hour, it takes a day for it to go from 70 to 50. Double the mass, it takes 2 days. Okay, so that's time constant of a building. The longer the time constant, the better in any kind of outage. And the outage could even be your heating system poops out, right? It doesn't have to be some massive event. But I used to live in New Hampshire, and occasionally there would be ice storms, and when they hit, they're very elevationally dependent. So my house was at 1,100 feet, and the big ice storm that happened, 25 years ago, which knocked out a lot of people's power, it just started up the road from me, right? I mean, it's like sort of 1,300 feet and above got hammered. So, and people called me and said, when do I have to drain the pipes? I mean, literally, because some people were out for a week and a half. All right, this is another slide from FIAS. Thank you again very much. This is a week in Chicago. I don't even know what the building is. It says Chicago _NV. Kat Klingenberg is so powerful, she moved Chicago to Nevada for a better climate. I mean, this is amazing, isn't it? So Chicago NV, it's heating outage resilience. It's not, you notice it's not a typo. It doesn't say outrage. We saved that for our politics. And it's a week. And you see there's 5 different cases here. The bottom dotted line is the outdoor temperature, which goes below 10 below. And those are 5 different cases of how good the building enclosure is, how much thermal mass is available. And you can see in the very best case, the building barely goes below 60. Okay, so that is a very resilient building. You can see the little bumps. This is like a real simulation, because when the sun comes out, if you've got a building that has some solar gain, then the temperature rises inside, right? And so these are good things. And the house that I built in New Hampshire in '85, I did something that was stupid as an experiment. I had the basement was mostly finished. I had no insulation underneath the basement slab. And I wanted that long-term connection to the ground. The perimeter is heavily insulated, the basement perimeter. We left for a month in December 1989, which at the time was the second coldest month on record. And I turned the heat off. And I had a friend come. I said, every week I want you to come and just make sure the house isn't freezing. House got down to 45 degrees. It had a fair amount of solar gain. It had the connection to the earth. So yeah, you don't get heat out of the earth if your house is 70 and the bubble beneath your house is 58 or something. But when the house gets colder than 58, then that energy starts coming back. So that house would never freeze. It just wouldn't freeze without machines. Okay, so thermal storage. Taxonomy is a word I don't really know what it means, but 4 syllables. Pretty good, right? So, taxonomy of thermal storage. Thermal storage could be either passive or active. If you've been in this field a long time, you might remember the Passive Solar Conference. I think it was 1980 in Amherst. And there was a presentation about passive solar and why it's better. And then the guy hits the slide and it says, so what's better? And it said, active. And then he goes, shit, wrong conference. And the next slide said passive. All right, so let's talk about passive thermal storage. It can either be freestanding, doesn't do any other job, or it can be integrated into the structure. If it's integrated into the structure, it could be masonry, it could be wood or some kind of bio-based material. It could be phase change, where the material changes from solid to liquid, probably not liquid to gas, but solid to liquid and back. If it's freestanding, it could be masonry. it could be water, and it could be phase change again. That's passive. We're going to look at examples of all this. Active, typically either masonry or water, but now the water is typically remote. It's not right in the space. If it's remote, we can move energy to the water by air, or we can move it by water, hydronic. Masonry, we can integrate it structurally, or we can have it remote. If it's remote, it's typically something like a rock bed, but people have done remote storage with CMUs. They've done it with pipes and ducts in soil. Plenty of ways to do this. If it's structurally integrated masonry, we can feed that masonry with air or with water. Now, I don't know if I've got every single possible thing here. Maybe I don't, but this is a reasonable start thinking about how do you do this. So let's look at some things. I want to give a shout out to my government and my tax dollars at work. The 3 passive solar design handbooks that came out of Los Alamos, 1980 and 1982. You can see that these actually are books that were used. Like most books are supposed to be leather bound and on the shelves, and you're supposed to look cool because you own them. These books are still useful because you know what? We got PVs, which were super expensive when these were published. We didn't have LED lighting or even shitty compact fluorescence. We didn't have electric vehicles very much. We didn't have the really cool glass that we have now. My first house I built in 78, 79, I built windows. Glass, 4 layers of optically clear Mylar. I did the math. I thought, wow, windows really suck. So I built windows, right? Because that was the weak point. I figured it was easy to make a tight building, easy to put more insulation in, but the windows sucked. So I built windows. Anyways, we have all this cool tech that we didn't have 45 years ago, but the physics are the same. They haven't been changing the physics that fast. Oh, and this link, and by the way, I have a PDF that I gave to Betsy, and so you can have all this nonsense for yourself. You can get PDFs of these. That's the link. Isn't that cool? That's your tax money at work. They waste most of it, but once in a while. All right, so let's look at some of these things. What are examples of passive, freestanding thermal mass? This is the New Hampshire Society for the Protection of Forests, building by Stu White of Banwell Architects, done in the late 70s. Cal-wall tubes, fiberglass tubes, 18 inches in diameter, filled with water. Each one of those suckers is 1,100 BTUs per degree F. That's a lot of storage. And they are directly sunlit, which is important. The very cool thing about water in containers versus masonry is this thing called convection. And it's natural convection. No gluten. It's organic. So the part of the container that's in the sun gets warm, and the water adjacent to it gets warm. And so it does this. So the water in there warms up, and the fact that it's 18 inches deep isn't a big impediment to storing energy. So this is, a kind of a functional way to do this. People have used these because the light coming through them is very diffuse, so you can do some cool things design-wise with it. In the same building, the Clear Story lights these phase change pouches over metal ceiling panels. So these are salts that change from liquid to solid and back at around 72 degrees, I think these were. And the sun is on them, so they absorb energy during the day. You get a lot more energy in a phase change than you do out of sensible temperature change of mass, because like changing water to ice is how many BTUs per pound? It's 140 about, right? So if you want to get 140 BTUs per pound out of water, you have to move the water a lot of degrees. But if you change it to ice and back, which is not that useful for heating your house, but might be for cooling, then you get a lot more. So phase change has a lot of cool aspects to it. The phase change pouches were over metal ceiling panels. The pouches, of course, have polymers in them. And what do we know about polymers in the sun? They go away. Yeah, they basically go away. And then what do we know about salts and metal panels?
They go away.
Yeah, they go away too. So these are all rusted to shit after about 10 or 15 years. So good idea, poor execution, but that's what they had. I guess I'll say, again, parenthetically, how many people here know who Eleanor Raymond was? Anyone? Betsy? Thank you. I'm glad there's someone. So Eleanor Raymond was a woman architect that was one of the early women modernists and one of the very few women modernists, and she was a great architect. How many people here know who Mariah Telkes was? A few more, right? So Mariah Telkes was a Hungarian chemical engineer. I don't know if she studied adhesion, Foster, but if she did it really good. Who was brilliant, emigrated to this country, and was fascinated by solar energy utilization. And there's now a movie, a PBS movie about her called The Sun Queen. And Mariah Telkes was brilliant and working in this incredibly male-dominated field. And Hoyt Hoddle, who is also kind of a name in the solar energy forebears that we have, basically suppressed her because she was smarter than him. Eleanor Raymond and Mariah Telkes did the solar house in Dover in 1948. And it was this really ugly fucking thing. And I know about this because I have a client who built a house on that site, and we tore that house down. It hadn't been occupied in years. It was really grim. They didn't understand a lot about separating that building from the ground. So it was really like moldy and creepy. But there was this huge solar clear story and tons and tons and tons of phase change salts. And basically the sun heated the phase change salts, and then a fan heated the house. And it worked for a couple of years, and then I think the container started to leak or something. So that house was actually one of the really early and probably 100% solar houses with probably a terrible thermal enclosure compared to what we even build to code today. So there's a history of this stuff. And I think that it's useful to know who went before you, right? So if you're thinking about solar energy, Norman Saunders, who Andy worked with, the Keck brothers, people did this stuff. And you can learn from what they did. You don't have to reinvent it all. Okay, passive structurally integrated. The Trom wall, named after Felix Trom, French. We call them mass walls because we're in Massachusetts. So Doug Kelbaugh's house was this iconic Trom wall house in Princeton, 15 inches concrete with a selective surface. So this is a surface material that has a very high absorptivity of shortwave solar energy, and its emissivity, its radiant loss in the long wave, because the temperatures are much lower than the sun, hopefully, is very low. And so I think this is probably an applied metal foil with a selective surface and an adhesive back. We're back to adhesion. See, Foster is everywhere. I actually still have a roll of this stuff, the selective surface foil. It's a nickel plating on copper. So this heats up during the day, and then it delivers heat into the building at night. And the chief reason that anyone would even think about a mass wall is that you can't keep adding glass to a direct gain passive building, or you get the building that just gets really hot and then really cold. We're going to talk about that in a second. So the mass wall delays the solar pulse because it takes time to conduct through the masonry. And you could tune these by how thick and what material, because brick versus stone versus concrete versus types of concrete mix have different conductivities. So you could tune these, and the only time I've ever used these is where combining it with direct gain. So this to me would be a horrendous place to live in. You know, I mean, this is not my ideal for a house, but I've done a building where there was a mass wall essentially below the sill line, and then direct gain glass above it. So, you know, it's something you could use, very rarely seen now. On the right, there's an image of it from a book, and it's interesting because it shows movable insulation on the outside, right? So once it heats up, the best case is you insulate it at night, so all that heat stays inside. It also shows it with dampers and allowing natural convection to go into the house during the day. That, to me, is a kind of a dumb thing to do with a mass wall, because the whole point of the mass wall is it's supposed to delay the delivery of heat to the building. So you don't vent a mass wall. All right. I want to take a little sidebar and talk about passive thermal storage. So putting mass in your living space and how you think about storing that energy. So the material, if you're selecting material, the parameter that matters is the thermal effusivity. And it is not a dimensionless term like thermal diffusivity. It is the square root of thermal conductivity times density of the material times its specific heat. So density of the material times its specific heat gives you a volumetric heat capacity. Heat it can hold per volume, which is useful to think about when you're actually designing a building. We think more volumetrically than by mass when we think about buildings. And thermal effusivity is the measure of a material's ability to exchange thermal energy with its environment. So how much energy can penetrate into a material is a function of how well it conducts heat and how much heat it holds, right? Both things matter. Let's look at a table of thermal effusivity of materials. So cast iron is really dense, 450 pounds per cubic foot. It has great conductivity, doesn't have very good specific heat, but the other things kind of make up for it. Heat capacity of 54 BTUs per cubic foot per degree F. Its thermal effusivity is 38.9, not 39.0, not 38.8. Decimal points, very important in these things. So if you make your enclosure out of metal, don't let the metal go through the insulation, okay? Underneath the metals are masonry. So concrete is less dense. It's way less conductive. It has a little bit better specific heat. And its thermal effusivity is a little under 6. And then you can keep going down. Gypsum plaster, softwood. Wood is not very dense or very conductive, but it has a high specific heat. So wood actually stores some energy. You can't use wood in very thick. You couldn't make a trom wall out of wood because its conductivity is crappy, right? So all this depends on how much in thickness, whether it's useful or not. So thin layers of material like plaster and wood can actually store energy, but they have to be thin. And so the person that tells you, oh, I got this great passive solar house, I built a 30-ton brick chimney. Well, the brick chimney is 5 feet thick. And if you put a sensor 2 feet in, you're going to find that the temperature does not change at all, right? So there are characteristic depths of materials that are useful. Like concrete, the first 4 inches does all the work, really. Like having 8 inches of concrete slab versus 4 inches. That will help your time constant, but on a daily basis, having the sun hit it and that energy coming back out at night on a diurnal cycle, 4 inches pretty much does it. But these less dense, less conductive materials have to be thinner to be useful. All right, pitches. Oh, no, I guess I'm going to do this first. These are old guidelines. And they may not be totally applicable today because our building enclosures are better. But remember, the glass transmission is lower because the glass is better, right? So these are based on clear double glass, pretty transmissive. If you go to a triple glaze, double low E, argon glazing, way better insulation, but maybe 2/3 of the solar transmission, right? So there's some balance here. These are probably still reasonable. You can't put more than 7 or 8% of your floor area in south glass without overheating the building if you don't have added mass. Over that amount, if you're using masonry, you want 5 or 6 square feet of sunlit masonry for each additional square foot of glass. This is really why a lot of the early passive solar houses overheated. You add 100 square feet more of glass over that baseline, and you need 500 or 600 square feet of mass in the sun. So if it's in the slab and you happen to occupy the house and you have furniture and toys and dogs and rugs, then most of that slab's covered. It's not even in the sun anymore. So if you're relying on convection to transfer that heat in the space, then you actually need about 40 square feet of these low thickness, these thin layers per extra square foot of glass. All right, I got this from Jacob. He is a Sachs maniac, as you know. So, straw bale house. How many people here have ever participated in a straw bale plaster party? Yeah, a few of you, right? It's like you keep pushing that shit in and you keep pushing that shit in, and it's like infinite. Like, where is it going, Jacob? Where is, like, there's no such thing as a ½ inch of plaster on a straw bale house, right? Keeps going in. So there's a lot of mass in this house. There's the wood. There's the plaster. It's not like a passive solar house, but this house has more mass than your typical wood frame house with a ½ inch of drywall, by quite a bit. This is the same thing big. So this is the Kern Center at Hampshire College, one of the early Living Building Challenge buildings, and it's heavy timber. That decking is 3-inch decking, polished concrete slabs. There's a lot of mass in this building that is addressable because there's a lot of area of it. This is one of the early earth-sheltered houses. Don Metz, best architect I ever worked with. And this is the Winston House in Lyme, New Hampshire. Talk about time constant. Whoa, I mean, like, the thing's got a foot of soil or more on the roof, so it ain't changing very much going up. And same with around the north, west, and east sides. And look at the roof. Look at the roof structure. Beams like 1 foot on center. Think about the surface area augmentation. That means bigger. 4 syllables. Well, essentially, the roof structure there is what we like to call crenellated. So there's a lot of mass just in the roof there. The floors are masonry. And everything around it doesn't change temperature very quick, because dirt doesn't change temperature very quickly. Don wrote an article in the, I think, 1979 Solar Age magazine, and he talked about, he is a very funny guy, and he said, you could use it doesn't have to be earth. You can use anything that you could pile around your building. He said, you could use creamed herring, but then some people don't like fish. And they published that. Okay. Modern version of this is a building that Andy and I worked on, so it's probably fucked up doubly. Two nerds are way worse than one.
It goes by the square of the number.
It goes by the square of the number of nerds, especially if the nerds are pretty square, and boy. So lab building in New Hampshire, CLT, floors, roof, and a bunch of walls inside are CLT as well. So again, the energy is not penetrating deeply into this on a daily basis, but this building has a lot of mass. And it's addressable mass because they're not covering it with drop ceilings and stuff like that. This is a super interesting project that Mike Brown has worked on. I worked on a little bit. This is Holland Moscow developers in Newburyport, Hillside Center for Sustainable Living, tilt-up concrete. And Mike told me this morning that they are doing it with hempcrete now. So they've way less embodied carbon. And these are certified, the first round was certified passive house. Second round missed it by air tightness, right? And then the third round is that they're building is hempcrete. So tilt-up construction, massive, lots of insulation on the outside, really long time constant building, right? And then on the lower right-hand corner is a snapshot of a building I worked on 30 years ago probably in design, the Bicentennial Hall at Middlebury. It's a big scientific lab building. It's 225,000 square feet. And Joe, are you here?
Yes.
So I showed this to you, my proposed wall section, and you said to me, that will be the last building standing in the state of Vermont. So the largest precaster in New England at the time, I think, I don't know if it's still true, was in Middlebury. So the fundamental construction here is tilt-up concrete panels that are 21 feet high, 2 stories in this building, 10.5 feet wide. Now, that's not a tough air barrier job. Where are the cracks? Oh, yeah, right? So then it's got a membrane over it. And then this was the first time I used rock wool. So we used rock wool, high-density rock wool bats in the cavity. And if I recall correctly, there was a code limitation on how big the cavity could be. And I persuaded them to fill it because the rock wool will drain. So there's 5 inches of rock wool, stainless steel anchors, stone veneer. The roof is a steel structure, obviously, but then taped gypsum for the air barrier, stress skin panels over it, so no thermal bridging, no ice dams. All these university buildings up north have wicked ice dams from either just rampant air leakage or more modern buildings with steel structure going through the insulation. No ice dams in this building. Slate roof. Like, it'll be there in 200 years for the second bicentennial, quadcentennial. Yeah. Anyway, lot of mass in that building. Precast. So this is a building that Andy and I, you can see us in that lovely picture in the lower right. Andy is wearing his ubiquitous black raincoat, even though it was not raining. It's just it's a thing. He refuses to take fashion advice from me, and I've never understood this. So this is a really cool building. Southwest England don't need cooling if you do it right? Because the peak dew points are not high. Maybe they are today, I don't know. So this is a piece of precast, the ceilings of each floor. They sit on Y-flange beams, and that shape is both structural, right? It's an arch, but also it's shaped so that the uplighting bounces off of it and down. The sound bounces up, because this could be a really bad acoustic environment. It bounces up, and those wings on the lights are sound absorption. Right? So think about the level of integration of the design team that makes something like this, right? The structural engineer, the lighting person, the acoustic person, the architect, they're all working together to design this building. And That's what we need to do if we want to make really good buildings. All right, that's my kind of wrap on passive. Active. Storage in active systems is usually remote, not always. The storage is often dispatchable according to need. Like passive, it's in there and the building's going to swing in temperature if you want it to passively absorb heat and then give it back. You don't have to do that with remote storage. You can get much higher temperature differentials. You typically need power to charge and discharge, or one or the other. Not always, but typically you need some power. So this is another building that, and these buildings, we went to Europe with a couple of other friends for 3 weeks to look at leading edge buildings in 2000, right? And when we came back, people said, boy, I wish I could get a grant to do that. And we said, we wrote our own grant, right? CEUs, we wrote our own checks. So this building is 35,000 square feet. It's hollow core precast planks. The space conditioning air is combined with ventilation air because they don't need a lot of space conditioning air because the building is super insulated. It's only 5 zones in a 35,000 square foot building. They don't change the temperature. There is not a setback. It's incredibly stable. The walls are CMU mostly for sound absorption, but again, more mass. We met with the facilities operator of this building, and he said, I've gone to the facilities design department. He said this in a British accent. I can't do that. He said, I told him, I don't care what the next buildings look like, but they have to work like this one.
Mark, what do you think the time constant is on that building?
Oh, geez. I don't know, 200 hours? Something like that?
What's the question?
The question was, what do I think the time constant is? And I'm going to say 200 hours or more, something like that. Super resilient building. And then the British did a study of all these leading edge buildings called the Probe study. This was the highest occupant satisfaction. So we went to a bunch of buildings that had gotten a lot of publicity. Rocky Mountain Institute was there touring at the same time, wrote a completely different report than us, because we talked to the people in the buildings, and like there was that building in Leicester that got a lot of publicity. Alan Short Ford did it. People hated that building. They hated it. It was uncomfortable. RMI was like, this is the greatest thing, we should be doing this. You need to talk to people in buildings. Okay, here's structurally integrated masonry. This is Dartmouth College, buildings I did with Brunner Kott and Dan Knoll. This is integrated hydronic. So what you have here is PEX tubing in a topping slab over precast hollow core plank. Now Dartmouth was building their dorms like this anyways without the PEX, because this is a really good way to have a very soundproof building, right? And then both the floor and ceiling are thermally active here. But the floor dominates in heating, convection up, and the ceiling dominates in cooling. And this is a key thing. The latent load is removed in the ventilation air. So the ventilation air is very dry, but you need a lot of ventilation air for such a densely occupied building, college dorm. You're not doing this like this in a house. You can't dehumidify the house in 100 CFM of ventilation air. But this, every dorm room gets a certain amount of ventilation air. A lot of air is moving around. All the latent comes out of the ventilation air. So here's a thermograph of the floor in one of the dorm rooms. And you can see, you know, that it's not too hot here, right? These are very well insulated buildings, triple glazing, 7.5 inches of polyiso on the roof over an air barrier, spray foam walls over the wall on the outside. So brick veneer. So you can see that like the floor is sort of 72.5 or something. You know, if the green is kind of dominant. Here's the ceiling, and the ceiling's a little cooler. It's just over 70. I learned something on these projects. We did an academic building as well as 500 beds of housing. And Dartmouth had them thermographed. And they called me up and they were ripshit about, look at all these, like, so look at that upper right-hand picture. All the colors are there. But look at the range of the colors. It's like not very much temperature differential. And I said, yeah, those thermograms show you that that building is really good. Like the lowest temperature is like 63, and that's the glass, right? So I learned that you can't just give a thermogram to a client. You have to manipulate it so they don't think you did a crappy job on the building. All right, active remote masonry. So that's structurally integrated, active. You can control the temperature. Obviously, the slabs are controlled, so they're not below the dew point, right? Because it'd be drip, 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 drip. But the point is, they're building it almost that way anyways. The additional cost is the tubing. And one of the ways I sold this to Dartmouth Housing, their branch that manages the buildings, is there's nothing for any student to break. Right? There's nothing in the space. And the second thing, which many of you will appreciate, is college dorms are known for having half the windows open. That is called, according to Henry Gifford, the window stat. I told them, yes, there will be people that will leave for class with their windows open in the winter. And when they come back, because the limited amount of heat that can come in through a radiant system, their room will be 40. Even a Dartmouth student can learn. Maybe. Okay, fan-forced rock bed. The design method for this is actually in one of the passive solar handbooks. So you too could learn how to do this. Freestanding greenhouse. This is building after many, many years. And you don't want to have mass in a greenhouse that you can see because it is competing with plants for light. So greenhouses want to be white inside. They don't want a whole row of black barrels at the back. I did one like that in 1979, and the plants all grow like this. Later. This is a house in Vermont in a very remote place. And the owners, this was a second home originally, and they said, when we come here, we want it to never freeze, and we want it to be comfortable enough that when we get there Friday night, we can go to sleep, light the wood stove, and wake up and it's comfy. So this house has a big rock bed underneath it, and big greenhouse, and then you can see the 2 layers of glass above, and it's what I call a solar attic. And so instead of taking the air out of the greenhouse at 85 or 80, you don't have a very big delta T. I want more temperature differential for the same amount of mass flow of air. So it comes out of the solar attic at about 110. Sealed glass fails eventually. So the greenhouse is double glazed sealed glass. The glazing in the solar attic, which is going to get hotter, is single solar patterned glass over a 3M very high transmission film that was an anti-reflective film. And that glass is just shingled with silicone in between. So there's no horizontal battens, there's no seals to fail, and that glass is still there, 35, 40 years later. Big fan takes it out of that solar attic, blows it down into the rock bed, goes both ways, comes back to the greenhouse. Super stable house, because the house is over 3 feet of rock. The slab is over 3 feet of rock, crushed stone. Here's a project that's on the boards right now. I'm not sure it's going to get built. It's another freestanding greenhouse, but what it shows you is the bottom image is the floor and the rock bed. So what we're doing here is the air comes down the center and it goes in both directions. And the reason is when you're designing rock beds, it's a trade-off between length and pressure drop. So you're trying to minimize the pressure drop but still have enough length that you get all the rock you need in it. So you're playing with the height and the width and the length. And so if we did this along the back going to the south, we wouldn't have enough back pressure in the rock. The other thing is rock beds have so much surface area, like semi-infinite surface area, that the way that heat is stored is a pulse. It doesn't heat up uniformly. You can watch it move through the day. You know, the stones heat, and so the return temperature to the greenhouse, if the rock bed starts off at like 65-ish, it'll be 65 all day till the end of the day, and then it'll be warmer, right? So it's not hard to design these, but it's easy to design them wrong, if that makes some sense. And I am probably one of the only people who has ever done more than one forensic engineering investigations on failed rock beds. One had too small gaps and too long, so they weren't getting enough air. And one was made with 4-inch stones, and the air bypasses through because there's too much open area, right? So you can do it wrong, but it's easy to do it right. How am I doing on time? Time check? 20 more?
Yeah.
Perfect, great. Because there's no clock here, and I can't see small things. All right, fan-forced water containers. Active storage, passive release. This is storing storing energy in water is great because for all the good reasons. Water's cheap, water convects inside containers, but using water containers like a rock bed is a non-starter. Like you can't put a bunch of soda bottles in and blow air over them, and it's because the air bypasses them. The gaps are too big. Does that make sense? It's different than a rock bed. So you're not looking for, you have to think about how you're going to get, if you're going to use air, how you're going to get the energy from the air into the container. This is a freestanding art barn is really what she calls it, with a greenhouse on it, a lot of PVs that feed the whole property, batteries in the small basement. This was carefully designed for daylight for art on the walls. And you see that cupola, which is extremely unfortunate because the client said, it looks too much like a covered bridge. You need to make it look more like a barn. So this building is top lit with a slit of skylight at the ridge, and I designed it to have a certain amount of daylight factor, and if you walk around with a light meter, the place where the light is most suppressed is under the cupola. So more glass doing less work, and if you want, I'll talk about that next year. So there's the greenhouse. You can see at the right-hand side of the image there's a duct. When it gets too hot in the greenhouse, the fan comes on. The fans in that duct run in the basement. You can see on the right a bunch of water containers, 5-gallon water containers. This is the only time I've used thermomass foundation. Anyone here work with thermomass? So this is a method where the foam in the foundation is between 2 layers of concrete. So the insulation's in the middle. And so we get 4 inches of concrete as part of the mass of this building, in addition to the slab. And then in this picture, you're looking at the racks of the 5-gallon containers. And the plywood that you're seeing in between are manifolds. So the air from the fan, which is sucking out of the top of the greenhouse, blows into these manifolds. You can see the piece of metal flex that goes there, the 8-inch metal flex. And then the plywood has a gazillion, which is a big number. It's not as big as Brazilian, but it's a lot, of 1/4-inch holes. So the trick here is you have to blow the air at the container at a high enough velocity to scrape the thermal boundary layer off and get the heat into the jugs. And you know, we put sensors in some of the jugs. It actually works. If you just blew the air across the containers, it would bypass the containers and you wouldn't get heat transfer. So the key here is how do you get air to heat transfer to containers of water? She said, I want this greenhouse to never drop below 50. There's no heating system in that building. One morning, we, of course, have data loggers there, compulsive measurer. It was 7 below. The minimum temperature that that greenhouse is seeing is 45 degrees. So that works. Just passive release. It comes back up the stair to the basement, which is open. How do I know this is going to work? Well, certainly a certain amount of crossing your fingers, toes work too. But you actually can calculate stuff like this, right? You can calculate at a given pressure how much air goes through a hole. You learn this in engineering school if you were paying attention. At the time, we did not have phones, so we had to pay attention. We had slide rules, so we learned where the decimal point was. Important. And we built this little test rig with a Fantech fan and a flow measuring device and flow measuring device over the piece of plywood with holes that's in this box, taped to the top of this box. And we actually proved that the math worked and we got the amount of flow we were looking for. And I did this with Brice Delune, who's this brilliant French tradesman that I worked with at South Mountain for 10 years. And the French train their tradesmen. Oh my God, he is so smart. He can build anything, but his engineering drawings, because that's what he is now as an engineer, are better than any engineering drawings I get from engineers. But he did the education of building physics, the real fundamental physics of, so when we did this, he was like, holy shit, like, how do you know that? It's like, engineering, fluids, So anyways, you can calculate this stuff. All right, active solar thermal storage. This is a house in Hanover, New Hampshire, mid-90s. Active solar, in other words, it is the where you see the solar there, not separate panels. I had hair. That's Jim Surtees soldering it up on the roof. Those are selective surface copper panels, solar glass. It was pretty interesting lifting 4-foot by 10-foot pieces of glass up to the roof. And tempered glass is so amazingly strong. And being a weenie and having to get the glass shipped, there's 9 panels there. So I ordered 11. The thing, we opened the crate, and 2 of them, you know what tempered glass looks like when it breaks, right? It's like these little pebbles. Like, we open the end of it and all this shit comes out because 2 of them were broken. Okay, well, I guess we don't have any safety factor here now. They shipped us 2 broken. And so what we have here is a 1,200-gallon tank in the basement. I can run it 80 degrees delta T. That's 800,000 BTUs, which is not a giga something, but it's a big number. And then it's a drain back system. So there's only water in the collector when the sun is on it. There's 2 pumps because it has to lift it high. But once the siphon is made going back to the tank, 1 pump drops out. And you can use a small pump. And then what you have here is a fan coil. So this is just a conventional first company 4-pipe fan coil with a chilled water coil, which are big, the A coils, lots of, because chilled water coils work at low temperature differentials compared to heating. And so the solar water goes in the chilled water coil. And this house can be heated at 30 below with 95-degree water. So that's a key thing here. You're looking at a house that's a foot of dense packed cellulose, oh my God, in the trusses, quad-paned heat mirror for the fixed glass, insulated fiberglass sash and frame windows with triple 2 low-E layers. So the Krypton, the house for 1994 or so, this is a pretty advanced house. I mean, Kat would say, kind of medium, but pretty good for 30 years ago. There was this IEA project, Advanced Solar Low Energy Houses, and this house did better than all but 2 of the entries from the 18 nations that were heavily subsidized and way better than the US entry. The Germans beat our pants off because they had hydrogen and fuel cells and electrolyzers, and as my colleague Anna-Greta Hestnes, who's a professor in Norway who was managing that task for the IEA, said, this is the highest embodied energy building per square meter that has ever been built. So the backup heat is a 50-gallon electric water heater, and that water goes into the hot water coil. So you can still pull energy out of both of those pumps can work at the same time, both of the coils can work at the same time, and you can pull that tank all the way down to 80 and still heat the house. You have to supplement it with the other coil if it's really cold. One of the things I learned, we modeled this house in Excel, and we tested all amounts of solar aperture and storage. There's diminishing returns that just kill you. Like the whole basement could be water and it wouldn't matter, sort of. You get this much more. But the other thing I learned is, because this building was heavily monitored for a few years, is that in very low energy solar buildings, the amount of backup heat every year really varies because it depends on how sunny it is and how cold it is. And one of the things I learned from Andy via Norman is that we have this idea that if it's cloudy, it's not cold. But Norman said it's kind of equally distributed. You know, you can't rely on the sun being there and it's not so cold, right?
Yeah, we had a 6-day power outage, very cold and cloudy the entire time.
Yeah, but that's Vermont, which is almost as uninhabitable as Duluth. So you know, our model said that this building would use, I think, 1,700 kilowatt hours a year for the backup. And of course, the backup, you can't really tell how much is going into hot water and how much is going into heat. The way it makes hot water is there's a immersed coil in the tank, solar tank, and cold water runs through this immersed copper coil, and then the 50-gallon tank. So you can't, you've got one 4.5 kilowatt element. That's backup for heat and hot water. You can't tell how much went to each. But the model said 1,700 kilowatt hours, and over the first few years, it ranged from 1,100 to 2,200. You know, it's just, at that point, it's the climate. So when people tell you that you can make an all-solar house, and I ran it in simulations. I'm arguing with a professor in Colorado right now, back and forth by email. He said, I'll send you the dynamic simulations. I said, you're using TMY data. It doesn't tell you the worst case that you have to encounter. All right, this is my last case. Another building on our tour. This is the Swiss Dots building, and this is annual cycle solar. So on the roof of this 280,000 square foot building, if I remember, are almost 13,000 square feet of active solar panels and an 88,000 gallon tank in the sub-basement. So, you know, in places where it's pretty cloudy in the winter, if you want to use active solar, you're going to have to store it for longer. All right. Oh, and I have this thank you from Fias and Al Mitchell. I asked Al to model for me a multifamily building with ice storage, but with ice storage as a load shifting off of PV, not an off-peak ice storage. So he did this. It's a 23,000 square foot building. It's Fias enclosure. I have no idea about the inputs. I trust Al. He's smarter than me. And here's his base electrical demand for that building. It's a summer demand. It's residential, so it has the dual peaks of people getting up and people coming back from work and school. And there's that ramp up that you'd have at the end of the day. And here's his mechanical design for this. Fan coil units, heat pump chiller, makes ice or hot water, dedicated outdoor air system. And in this graph, you see the PV generation. The dotted light line near the top is the conventional electrical demand. And then the heavy line that's kind of an orangey line is the depressed demand by making ice during the day with the PVs, the first part of the day, and then using that ice, and the blue line is shutting the chiller off. Now, I think that actually, I didn't get to work with him enough on this. We want to shift this a little to the right, but it shows that this is a viable concept. You could use ice storage to shift load in cooling. All right. I have a few minutes left. I'm going to try to run through this. I have a client who's a little bit nuts. I'm looking at you. He wants an airplane hangar for his airplane. He wanted maximum consumption of on-site solar energy. But he's got a building that's got a low slope roof and it doesn't face the right way, and it's just the lot he's got. So hydronic radiant floor slabs make a lot of sense for hangars and garages and public buildings. Andy's done a bunch of stuff like this for a lot of reasons. Air-to-water heat pump, or Andy's been looking at ground source instead to keep the demand lower. Very interesting work he's been doing on this. I did a brick-in-a-box Excel model to inform the sizing of the storage, because I want to use the air-to-water heat pump to store some of that energy in water. Because I'm already working with water. I got a hydronic radiant slab. I've got an hourly model of the gain from the PVs. I've got an hourly model of the load of the building. It's more complicated. I've got all these other loads built into this model. And I build an Excel spreadsheet with 8760 hours. I've got the heat pump COP off of the manufacturer's data based on outdoor ambient temperature. So that's varied as well. And what I can vary here is the size of hydronic storage, how much PVs I have, and what the limits of the storage tank go to. Like, how low can I use the water temperature and still be usable? How high can I store it in that tank? And this is kind of a glimpse of what the top of that spreadsheet looks like. This will not be on the quiz, don't worry. And with 1,000-gallon storage, sort of like a small septic tank, we can use 54% of the PV that's generated on site, which is roughly double. And this is a non-optimal PV. Like, if this faced south at like a 40-degree tilt, Jason, then it would be a lot better than that. But even as it is, you can shave a lot of the energy that would be going to the grid and back in. So here's a bunch of cases. The first 5 are one slope of the roof with PVs, and the 19 kilowatts is enough to make it 0 net energy annual. And there's the storage from 0 to 10,000 gallons, and it shows how much PV energy is used contemporaneously. In this particular case, 7,900. How much is stored in that water and to be used again? How much gets exported and how much gets imported? And the interesting thing to me here is the first 1,000 gallons does most of the work. You get to 10,000 gallons and you've added 1,000 kilowatt hours storage. So this kind of analysis to me is important. And I want to say something that maybe I shouldn't say, but I gave this presentation at NESE, and at NESE, the Building Energy Conference, they curate. And the people there said, my curator said, this isn't really that interesting, and it's not really for our audience and stuff like that. So I'm going to just say, fuck that. People need to learn that everything that you might want to do is not in a piece of canned software. And everything that makes sense is not in an incentive or certification program. So this is a pretty unusual case, but Andy was talking about a case where he's got fire protection tank that he's already got to buy in this job. So think a little outside the incentives for this. Okay, you're always going to get, at least if you're in New England, a winter trough where there's just not enough energy coming in on a daily basis to handle a load. I did a very quick and dirty version of this, adding some battery storage. So now I've got thermal and electrical storage, and I drove that with the equivalent of 3 Tesla batteries. I drove that from 54 to 79% used on site. Again, very non-optimal roof orientation and pitch. And then finally, the last thing I want to say is that Bristol and I worked on a big house that was off-grid on Martha's Vineyard with a heated pool. I just work here. I'm an engineer. The house has 32 kilowatts of PV. It's got 138 kilowatt hour of battery storage. It's got a backup propane generator. The same kind of model was done. It's the same kind of Excel model, but it includes the backup generator because there isn't the grid. And one of the things I learned, and I think the reason you do this stuff is, I was talking with Blasnik Sunday night. You do it first and you look at the results and you say, these results make sense. And if you're me, most of the time they don't, and you've made a mistake, and you find the mistake and you fix it. And eventually you get to a point where the results smell right. You know, okay, this makes sense. So what I learned here that I never thought about before is if you are an old person who's done solar hot water, I'm looking at a couple I know, what you learn is that sometimes you set it up with a timer on the electrical element so that it doesn't come on at like 8 in the morning and heat the tank up so then you can't put more energy in from the sun. Because when the electrical element comes on, it's going to heat the tank up to the set point temperature because you don't heat the tank halfway because people get pissed off with 80-degree showers, right? So it's an all or nothing choice. Generator is totally different. I never thought about that. So one of my settings here is, and by the way, this is the battery. This is how full the battery bank is through the year. And so it's worse in December and January, but you see some places in the summer because of the pool where it goes down. What I learned is that you have to set a generator charge limit on the battery bank. Because when the generator comes on, because you've set a discharge, you don't want the battery bank to go below like 15 or 20%. But when it comes on, it doesn't have to fill the battery bank. That's stupid, right? So I never thought about it, right? But now I know I have to have that put in as a limit because that's going to calculate how much propane I'm using. And then I start to play with that. It's like, wow, this is pretty interesting. So you actually can learn stuff. Even when you're old, you can still learn things. It's harder. It's harder. Okay. So here's a bunch of cases modeled. This is early on, before we've actually sized things. But the horizontal axis is kilowatt hours of storage from 0 to 120. The vertical axis is gallons of propane per year. And the two lines are 20 kilowatts or 30 kilowatts of PV. And the dotted line is, if this house had no PV and it was on the grid in Massachusetts, what were the emissions from the energy that it used? So you can see that an off-grid house, PV, can make more emissions if it has to be backed up with generator. In other words, the generator is so much dirtier than the grid that I'm not a fan of off-grid houses in general, but this was a job we had to do. And you have to get to 20 kilowatts of PV and 40 kilowatt hours of storage before you dip down below the emissions from the grid only, right? That's important to me. So where we ended up is close to the end of that lower red line, and we're using about, I think, 300 or 400 gallons of propane a year. And by the way, the first weeks that house was occupied, we were on it and really looking at how is our model, is it validated? And it was within less than 10% off. And then it started to go up again. And the freaking pool contractor, you've got these wonderful inverter-driven pumps that are variable speed, and we would turn it down to what we really needed, and every time the pool sub showed up, he turned it up to maximum. So we could just see it in the data.
Take off the knob.
Take off the knob. All right. Oh, I want to say one more thing while Joe's running around. So I showed my house and I showed that heat, you know, the amount of heat that the house used. So that house was what's called a deep energy retrofit. And there's an increasing discussion about that they're not worth it. And I want to shout out to FIAS for their new Revive program that they unveiled last night. And I want to say that you should always pay attention to the difference between financial and carbon payback. So my DER cost me a fucking fortune. And using the BEAM tool, for which I am a beta tester and people should really look at, talk to Jacob or me, my carbon payback on that DER is 2.2 years, right? So DERs make sense done by people who think.